Yeah, Dr. Dattaji Shinde. Yes, sir. Okay. So over to
Yeah.
you, organizing team. Over to you, organizing team.
Yes, sir. Good afternoon. Good morning, one and all, and welcome back to the second session of today. It's a great honor for me to introduce you all to our eminent speaker for this session, Dr. D.K. Shinde, who will be taking this session on 3D printing of polymeric non-composite prospect and challenge. He is an associate professor and the head of production engineering at Viramata Jizabai Technological Institute, VJTI, Mumbai. He has a vast experience of 19 years in the industrial production engineering academia. His research field includes process modeling in composite nano-engineered materials and nanotechnology, electrospinning molecular dynamic simulations for polymeric composite materials, multifunctional materials low-cost composite manufacturing, mechanical characterization of materials, computer-aided design, finite element modeling fatigue, impact modeling, and testing of polymeric composites. He has received various awards which include the Best Startup Award by World Trade Center Mumbai and Chamber of Commerce and Industry, Best Dronacharya Award for mentoring innovation products for Smart Navigation Band at national level entrepreneur competition, Dr. Kennedy Scholar Award, North Carolina A&T State University. Over to you, sir.
Yeah. Good morning, all of you. Let me share my presentation, and then I will take you through today's entire session on 3D printing prospects and challenges. Can you see my screen? Or organizing team and participant, can you give me the feedback?
So screen is visible, but not entirely. Maybe you have to share entire screen and then maybe possible.
Can you see full screen?
Yes, sir. Yes, sir. We can see that. Yeah.
Yeah, so once again, I welcome all the participants for the day 3 of this ATAL FDP on 3D printing, which is a very important one of the training program launched by the AICT in the thematic area 3D printing. One of the fifth area in which the 3D printing comes in the today's technology development and the manpower development by ATAL Faculty Development Program Academy from AICT Delhi. So I welcome all of you for this day 3 session. So before I start my session, first of all, I thanks to Professor Kiran Bhole sir for inviting me as an expert to deliver a talk on 3D printing of the polymeric nanocomposite prospects and challenges. So I thank you, sir. Also, I thanks to the organizing team and the institute, Sardar Patel College of Engineering, Andheri, Mumbai, for giving this opportunity to share my some of the views and the material what we have created through the research at VJTI and my past research at North Carolina A&T State University, USA. So let me take you through the quick presentation. If any interruption occurs, let me know either by the call on a telephone, or you can ask me by audio also. So that is the first instruction. And second thing is, if you have any question, kindly hold your question. I will take your all the questions at the end of the session, and then I will answer your queries. So meanwhile, the noise and all those things, try to avoid any background noise, so that all the audience can listen the session carefully. With this few instruction and announcement, let me take you through the today's presentation. So I will be taking you through this important 5 aspect of 3D printing. First, I will talk about the nanotechnologies, past, present, trend, and growth. because to understand the nanocomposite, you need to know little bit, or refreshing of the nanotechnology, nanomaterials, and how those nanomaterials we can take in the, our material to develop the 3D printed parts and structures, whatever we want to develop, and how the those nanomaterials are playing an important role. Then few of those published research, whatever we have done so far, effect of carbon nanotubes and graphenes on ABS for the mechanical and electrical characterization, which are developed and produced by using the fuse deposition method for the polymeric material. Then one of my PhD scholar who is submitting his thesis, he is working on the infill patterns, role of the infill patterns, and how infill patterns with the percentage infill with and without carbon nanotubes, again in the ABS as a base material what we have selected. I will be talking on that one. Development of the two remaining two important aspect what I'm going to discuss, very decent prospect and challenges, what the aerospace and big BAM, what we say, the big area additive manufacturing, the large scale additive manufacturing for the high strength fiber reinforced composite to develop heavy structures, and what are the challenges, what are the prospects, how it will be helping in the aerospace when it go for the moon mission or maybe for the Mars mission, or maybe international space stations, how our astronauts can use this technology and develop the quicker those parts, and what are the challenges they may face, the early stage uh, continuous fiber 3D printing development from the Lockheed Martin SpaceX aerospace. I will be talking to you. Just one of the published research in the SAMPI 2021. If I get time, I will talk about the nano fiber synthesis and those applications if I get more time. So let me introduce myself. If you are from all over the India, we are located in the central part of Mumbai. This is what we have our Gateway of India, known to in Maharashtra, western side. This is the VJTI 17.6 acres of land established in Victoria Jubilee Technological Institute in 1887. Now it has been become the name as a Veer Mataji Jabai Technological Institute. Acronym remains same. In 1999, they renamed the institute. I did the PhD from North Carolina State University from USA. I work in the Joint School of Nanoscience and Nanoengineering, a big center for the Greensboro campus of North Carolina University system. So this is what I want to share something, but I want to just acknowledge my previous research also. So VJTI, well known. Just I always talk about my institute also wherever I go for any talk and deliver any talk. So we offer a diploma, UG, and PhD program in respective branches. So we have the REI ranking 5th in government colleges in 2020. NRF ranking of the currently published is 82 among the engineering group and technology group for the 2021. 82 is our rank of the institute. I come from the Department of Production Engineering, which is established in 1959, and then subsequently after DIE program. In this department, our department is having UG, PG, and PhD program in the production engineering. Few of those intakes 16, UGP established 73, production in 88, and production engineering 2002, and currently we are running one more program. So that's it about my introduction and my institute. So let me go through you quickly through what is nanotechnology. The man first who gave the idea about there are lots of room at the bottom of the plenty of the room at the bottom. Who gave the first rate to know what is the nanotechnology? The Richard Feynman. He thought initially how we can use that smallest things at the nanoscale, like maybe a few angstroms, 10 angstrom, 15, 100 angstroms of size, and how we can keep playing about that one. So he gave the idea in the 1959, and people reached the in the search of finding such kind of material technology system development. So nothing nanotechnology, if you are new, so it is art of science of building the stuff that does stuff at nanometer scale, like 0 to 100 nanometer scale. We treat as a nano scale synthesis, manipulation, development. So the Richard Samley in 1996, he received the Nobel Prize, and he developed such kind of small device materials at the scale of 100 to 0 to 100 nanoscale. So few of those molecular modeling has been shown over as an engineered DNA strand, RNA tiny motors, and semiconductor metal junction formed using two carbon nanotubes. So this is so purely, if you want to know what is nanotechnology, is 1 billionth of meters, or you can say 10 to the power minus 9 of meter is equal to 1 nanometer. If a person, how small in size and shape, if you want to think in quickly, if a person can walk in a day, like about 32 kilometers or maybe 20 miles in a day, if you shrink the height of the person, average height is 5.5 inch, you can say 5.6 inch or 5.8 inch is the average height, you can say. If you shrink that 5 feet, 5 inch person to a smallest size, like whatever your 10 rupees bill or maybe $1 bill, $1 bill is the same size. The smallest, if you make how long that person can walk, the same kind of concepts comes in the mind when you go for the scaling down to know about more about that matter, things what happens at the scaling down. If you shrink the person from 5 feet 5 inches or 6 inches to let's say the 1 inch 3 inch or 2 inch of a person, so how long he can complete that distance is just imagination. So if you see, it will take a 24 hours. Let's say the 3 inch of note size length is a 3 inch. So the same person, if you shrink it or make the smaller size of the same person, so he will take to walk the same distance, about 32 kilometers or maybe 20 miles, it will take almost 24 years. That is how the size matters, how small size is playing important role to make those displacement or dispersion of that particular particle mix. So this is manipulating. It's the science of manipulating atoms, molecules, make the new materials and devices, and lots of things are coming from science, engineering, technology, which make the interconnect, and few of those which came in the early stage of development of the material. Maybe your bucking, came with the buckyball, and then nanotubes came, and then you have the nano ribbons, and those kind of nano ribbons can be now widely been used as a graphene, to totally a plain graphene sheet, to the formation of different nanomaterials. And if you compare the size of the new human, which is nanometer 60 to 800 micron size of the person, if you go with the comparison with the smaller size to understand more about how the and which nanomaterials we can use in the 3D printing also. So from the right to left, if you go from the tennis ball, 10 to the power 8 of nanometer, then you have 7 as a 6 as a period, then cancer cell and bacteria and viruses, what we are suffering in the pandemic. COVID pandemic is around 400 microns size, that comes in the the funnel of your nanotechnology, where all these materials can be an effective tool to capture such kind of viruses and work with the biological nanomaterial. And then you can go with the lower size, where antibodies is having 10 nanometer. If you go the glucose one molecule size, which is 1 nanometer, and then if you go with the water molecule H2O, which is having point 0.1 nanometer size, like that we have the scale. But there is the molecules and atoms become more stable due to its energy and applied manipulation or stabilization energy. It remains as it is in the range of 0 to 100 nanometers, and therefore people keep developing those material in the same range and above that one, to use it in the conventional material to enhance the mechanical, electrical, or thermal properties for various applications. That's the main idea to understand about the nanomaterial, where I will be talking how those nanomaterial can be helping us to make the 3D composite, nanocomposite. So few of those scale things are also shown over here to understand more better, and how the 3D printing can develop those kind of using top down approach, or you can use your bottom up approach. Both are used in the nanotechnology, but our 3D printing is a bottom up approach. So layer by layer we keep developing or cutting those particular structure, and we build the entire structure and then provide those connectivity and make such kind of devices, which are shown over here by comparing the natural things available in the nature and things made by the person on the right hand side using the head of the pin, or your micro electromechanical DMMs devices, or maybe you can have your pollen grain ray ribbons, and right side here the challenges to develop such kind of molecular models and stabilize the model which comes in a picture. So DNA, RNA are the lower side of the our blood group, and what we made up from the DNA, which comes in a picture over here. So this is comparison how small hair look likes and nanofibers look like at the bottom level. Few of those nanotechnology, past and present, which National Initiative for Nanotechnology talk about United States in the early stage. I'm going to share few of those slides. Nano 1, Nano 2, and Nano 3. So 2000 to 2010, it was Nano 1. 2010 to 20, whatever the system material so far been developed is 2. And now we have entered in the era of 2030 era, where we are expecting much more expansion of this technology and integration, and augmenting the technology to develop the new devices and materials in the early stage of fabrication using the 3D printing. So molecular printing, or maybe drug printing, are the various aspects coming in the 2030s era, where 3D printing have the challenges and very high prospect. That's what I'm going to cover in few of those coming class slides over here. So those fundamental and all those, I'm not going to read those things, but what I want to say, where we had at the early stage of 2000, we create the only the material has been developed, few tools has been developed, and then it comes to the assembly of the integrating parts, and then spin off came with the current 20 to 30 era, where we are getting the new nano system materials, and some of those businesses are coming with the 3D printing and developing those materials, structures and devices at your own backyard, or maybe in your own house in the next coming 10 to 50, 20 years. And that is what going to happen, and nanotechnology will be helping. You can print your own drugs, take the mixture, and you can print your own drug, and it will mix in such a proportion and develop your peel, what we say the tablet, maybe in the elliptical form or maybe circular form, and then it will harden it, and then same peel will be available with you. So you just need to fill those drugs in the fillers, and it will be printing your drugs. If you need to your child, you can print the same drug at your home. If you need to your older age people or middle age people, you can print at your home and you can get it. No need to run to immediately to your medicine shop. So that technology can be coming in terms of the 3D printing. So many other things are coming, but I'm not going to talk. So the new product and applications have the big prospect as a revenue generation in the trillions of figures. So therefore, people people are continuously working in that area. So few of those inspirations which comes with the national nanotechnology initiatives, which make the people vision inspired basic research, and now onwards the people are moving from the next 30 to 2030 with the convergence of knowledge and technology for the societal development. Few of those breakthroughs which came through the nanotechnology, so those are not important at this perspective, but let me go with these slides, which came with the 2020 Bill Clinton brought that initiative, national Nanotechnology Initiative, and then it was pushed by the technology pushed by the next president, W. A. Bush, and then subsequently Barack Obama took over, and the the technology development using the nanotechnology was one of the boost. And now after the Trump, the technology has taken a good shape, and currently the Biden is also making more, supporting and expansion of this technology for human and societal development through the nanotechnology. So few of those, one, two, three. So we are at the area. We are at the three technology decades. So here, what the nanosystem, and these are coming uh, for the discussion in this one. So these are the way how we can develop those, platforms and projects can be coming. So few of the nanotechnology which emerge with each of those. So I will exclude this one, since we will be having a very less time to talk on that one. So uh, let me take you through the those expansion with the your particularly in 15s to 2013s, what hierarchically interconnected word is using the nano, that really played in the year of 2020, and now the people are accepting the few of those areas like brain to brain communication, so non-instructive brain to brain construction. Few of those children are suffering from the brain disease, can be one of the way which nanotechnology will be helping them to make. So still these are the developments. So the technology wise, the papers which are coming, so lot of scope to develop the new material using the nanotechnology, and you can immediately have good impact factor and good chances to publish in the high impact factor journal. So this shows the indication of the top countries: US to Japan, European, and China, how it has been grown with the publication record. Similarly, what the materials they are using also, so few of those materials are noted, like technology-wise, names, devices, quantum dots, molecular motors, STM, AFM, molecular models, and atom models, and self-assembly. So if you see the self-assembly and STM-TM are helping to make most of the publication and bring the new technology or manipulation of those nano atoms at atomistic level or molecular levels are coming. So in the electronics area also, the quantum dots and quantum wheels are playing important role to miniaturize the technology to develop the 3D printed parts at very nanoscale level. So the material which emerged with the graphene as one of the top material, and its allotropes, what are the coming with the carbon allotropes in the form of graphene, carbon nanotubes. Then you have the bucky ball and other graphene sheets plays an important role. So some of those have been shown with the rising the publication with the starting of 82 to the 2020, and those contribution of the journals, again piping, US is going ahead with those journals, so we need to also contribute in publishing such a high impact journals. Worldwide growth is also, it's substantially or exponentially increasing the growth by filing the patent and approval of the patent in the few top countries. And similarly in the nanotechnology area, if you work, you can have better opportunity and to file the patent very immediately for process development, product development, material development. That I can encourage all the participants to work on that, and you have the larger opportunity as a part of Institutional Innovation Council of AICT and the Department of Education of Government of India. They are looking for more patents from the faculty and those ones. So these are the prospective way of having the growth in the coming years of 20 and 20 onwards in terms of the revenue generation of the indicators of the this one. So the material development plays an important role. Therefore, the all the systems and devices what we want to develop using the nanotechnology, it's not like only the manipulators like what STM, AFM, or STM, or maybe your helium ion microscopy. They are not going to build it all those things that but you have a lot of scope to develop the existing or conventional things to make the better performance. And therefore there are the only ways left to use those nanotechnology ingredients, whatever we have developed in terms of the nanomaterials, use those materials, and therefore in the 20 and 20 onwards, the nanotechnology is helping us to develop nanosystem by design. That's how our nanomaterial, what we print using the 3D printer, will be also coming in this area, and therefore I'm discussing all those things to know more about the material growth and prospective way of generating the revenue also over here. So therefore, the world is looking for getting more and more in the form of your materials in each of those area, continuously increasing. So in the 35% growth in the material development, and still it is going to be increase in the coming days. And some of those publications were, those 5 countries is continuously increasing. That is little, introduction about the nanomaterial prospects and technology, introduction of nanotechnology, nanomaterial. Now, how we can use those nanomaterials? So this is a paper published in the 2019 SAMPI international conferences and converted into technical, Scopus publication. So I will be talking on the mechanical electrical properties of the carbon nanotube based ABS. So acrylonitrile butadiene styrene, which is what we say the ABS material in the market, and mixture of these two we treat as a nanocomposite, and how we can improve those properties using the best way to play with the all polymers, which are thermoplastic or maybe thermoset polymers. So we can go with the developing those material using the fused deposition modeling method, what we treat as a FDM processes. So those things I will be talking. These are the quickly concepts. So let me overview and explain you the fused deposition modeling. So it's a layer by layer deposition, of material to build the structure according to the what CAD file and model we have developed. So slicing using the converting the STL file, all of you know, and then those STL file, a thin layer will be taken from your extruders and that printing head. You will be having this is a general view to a platform on which you will be having a support material first, and using the dual extruder printers, we can connect it. We can have the two spools connected. One is a support material, other is a printing material. So this printing head will be depositing, and its height will be adjusted. So it will X, Y, and Z direction, all three direction. Motion of those extruder has been provided. So this FDM typically, like most of those available, the wire diameter or filament, what we say is 1.75 millimeters in the form of a coil or a spool, which will be passing through this side. In the extruder, the material will be melting, and then we will be depositing and suddenly curing. So curing is very important. Solidifying, or maybe in thermoset we say the curing word. So those things plays an important role for the 3D printing to build the structure. And then few of the techniques like Mark Forge and other guys, what they are developing of Strata, they are developing the new printers of the industrial use. They have the very high quality of materials, what they customize themselves, and they start printing. Nowadays you can print on the surface with the all text material, like let's say you want to print like VJTI on the surface with the color only. So the same kind of spool you can provide the material, and you can print it instead of having the painting or maybe stick around that one. So those kind of material developments are in the right now going on in this era, and we have a lot of opportunity to use. Let me just show what are the things people they are just build those structures using 3D printings, maybe starting from your small geometrical shapes, sizes, what we look for to bring in the life, like gears are widely being used, levers, gears, and some of the toys, what we can say. Then construction, you can say the medical industry is a big big scope right now. Few of the people who build the heart, how we can run that heart. If this material is biocompatible, like what the heart we have, the same material if you develop and give the pulse and keep running this, diaphragm going up and down, so the pumping of the heart can come here, start. There is a way to develop artificial pump. Only the signal is the only issue. So mostly the functional material, if you have provided and the signal is given through our neurons, and that much volt has been given to the multifunctional material or smart material what we are going to use and print a heart. It will definitely work like your natural heart, but still the many days to go to develop those things. A few of those, like developing the aerospace components, I'm going to take few of those case studies. So if you look this figure, this is a published paper in 2017 from me and my group. We have published the review paper in that one. So this is how we can see the transparent 3D view of the platform. The extruders are coming with those depositing on the uh, your plate, whatever the support plate, what we say the substrate in terms of your deposition. So the electronic circuit, and here the simple frame. Now people are assembling and having their own frame, maybe less than 12,000 or less than 10,000 also right now. So what it does, like process, we have the component. Typically, we have the component like, let's say, the C kind of bracket. So how do you create? So we create the 3D model and then we slice it using the STL file. So stereolithography, those files we convert, and those CAD file we give to the our processor, and then accordingly your M code, G code and M codes are created, and accordingly your X, Y, and Z, those motors will be giving the motion to the your extruder, and motion will be helping us to deposit the layer to print 3D printing like this one. The typical way of looking over the stereolithography is you may be having such kind of simple built platform where the height plays an important role. What is the height of your structure you want to develop? So those layer of deposition and the sweeping of, in the sense what I have shown in the previous figure. So the moving left to right, front to back, up and down. So those motions will be coming, and those whatever the lenses are helping to feed the material will be coming over here, and you will be depositing, and using the UV light or maybe laser, you can simply cure it in a short duration of time, and you can make the strong bond with the bottom layer with the deposited molten form of the polymeric material. So this is how the photopolymer can be used to cure using the like UV light. The photolithography, how the positive resistance, positive photolithography or negative photolithography. So photo resistance material get hardened, and accordingly the liquid polymer also have the effect of curing faster using the UV light in that case. So if you look over here, the FDM process, what I'm going to use in my process also to develop my nanomaterials is the similar kind of depositing the material with your substrate. So build platform, then you have the support, what we call substrate, and then you keep developing. So these rollers plays and very important to feed the material through this to the extruders. So in these extruders, we would have the heating zones where which will melt, not immediately the in the form of liquid, but molten form it will reach, and those nozzles will be allowing to deposit, but chances to get clogged. So those challenges and taking care of that self cleaning or a certain deposition layer also is a cycle has been operated in the today's printed technology, right? Or develop the new printers like that. So another way the people are developing the laminated object, what we have the fiber laminated composite or fiber reinforced polymeric composites. What we have conventionally, we lay down the our fiber view forms, we stack inside the mold, and then we infuse the resin, and then we build our composite panel, or maybe the structure what we have. So that is the way. So but there are lot of tool cost is involved, material waste is involved, as well as the chances to exist some of those voids, and manufacturing cost is very high and productivity is very low. So therefore there are people who are developing right now the laminated objects, like what how we can use it. So the roller complete roll is coming over here, and then you can keep printing, or maybe developing a step by step and build the structure also. In this particular image, the laminated object, how it can be manufactured by heated roller, and then you can print it, and then the wasted roller will be coming like this. So this much material can be again go for the recycling, and you can keep using. Again, we pass the laser or UV light, and we can create those mask or transfer those particular object on the uh, substrate like that one. So this is how little bit fuse deposition modeling will be helping. In the simple way, people many times they talk about additive manufacturing or 3D printing, but now the word is moving to understand the simple word with the 3D printing rather than additive manufacturing. But it is a part of the additive manufacturing. So we develop everything using the bottom-up approach. So in our lab also we have the 3D printer divided by zero. So this model we have used to develop our material. So what we have done in this one is we added certain weight percentage of NWCNT to customize our spool, and then same customized spool has been used on the 3D printer divided by zero, what I have shown over here, active soft, and then we printed the material to be tested like the one kind of shape for the tensile, rectangular for the flexural, and other shapes according to ASTM and ISO standards, to print the material and test it rather than wasting the material, so as to analyze what are the mechanical properties has been built by developing such kind of material with the thickness which what we are interested over here. So styrene ABS is a copolymer made up from the polymerization styrene and acrylonitrile in the presence of polybutadiene, and therefore this material becomes like a rubbery. It has a shiny in shape and impervious surface, and therefore it has a resilience to the low temperatures, and it can act like a one of the improvement in to have the impact resistance, toughness, and heat resistance. Because of these four important property, ABS is widely been accepted in the automobile industry in the dashboard and interior part, and therefore it has been motivated us to do the 3D printing of nanocomposite and see what property we can improve in this one. So here, what we did, the same method we utilized. So in our experimentation, what we did is we selected the three important weight percentage: point 0.1, point 0.2, point 0.3 weight percentage of multiple carbon nanotube to mix it. So what we did, we have the vendor at Nasik, and solid space technology at Nasik. So this is a rotating mixer. We have the pallets. Generally, all the polymers, manufacturers, they give in the solid pallets, small, maybe like 5 micron or 10 micron length of the small pallets, having the smaller diameters, which can easily melt, and you can create any kind of wire, or you can create any shape and size using the different mold technology. So in our experiment also, we had pallets of the ABS. They were looking like a white in shape. So what we added, that three important weight percentage over here. So point 0.1, point 0.2, and point 0.3. So these three pool we want to manufacture. So we mix with the point 0.1 in the weight percentage in the pallets, and using the rotor mixer we disperse the multi-wall carbon nanotube which look like a powder and having a smaller diameter length. My aspect ratio is also low, and that was after mixing it was looking like this one. So the all the surface of the pallets has been occupied or coated with the multi-wall carbon nanotubes. Now this mixture will be poured in the hoopers of the extruder machine where it will be melt, and it will pass through the different heating zones and cooling zone, and then at the end extruder will produce our customized spool. This is what the layout they have laid down over here. This is the hooper where we mix the material like this. So cortex purging emulsion mixture they have, and then it passes through the first tank, then second tank and third tank, and then finally the spools were coming out and they were pointed out like this. The actual view of the extruder where the all heating zones were coming. So this is the end over here, where the extruder screw will be rotating. uh, you know the molten material will be forwarded due to the screw motion, and at the end we have the die of having smaller size like 1.75 millimeter of diameter of the spool is required. So that die will be extruding the material, and we will getting the continuous wire that will be kept in the water bath, and then we will get the sudden cooling of the wires with the diameter of 1.75. That was made with zero point 0.1, zero point 0.2, and zero point 0.3. So three different spool we manufactured using this industry located at Nasik, and then those the parameters what we obtain at the 3D printing. So this is the specification of our 3D printer, having printable area, then acceptable filament diameter, extruder diameter, and then from the filament, what it passes through the rollers, what I have seen over here, if you look over here, some of the rollers which rotate over here. So this is minimum what we can accept to pass through that roller. So this is what the 1.75 extruder diameter is 0.4 millimeter, and then two extruder we have, and then printable accuracy is 100 to 150 micron, maximum print speed 200 millimeter per second, and minimum maximum travel is also mentioned, and then laser precision is zero point 0.1 to zero point 0.3 can be obtained in this. So once this is printed like this is a dog bone shape. So the first we created the CAD file of the dog bone shape. Then that CAD file with the length, width, and thickness, we converted into STL file, and those STL file with the simple pen drive we uploaded in the machine. We install our spools to the spool holders, and then the wire passed through the nozzle and it was ready to deposit. So this is how it was depositing the 3D printing printing of those. Black is nothing but we have added the carbon nanotube, so this is black, but natural ABS will be white inside. So that I'm going to show in the coming slides. So we printed important three two specimens or coopers, you can say, tensile at our laboratory, flexural, and then we did the electrical resistivity test of the wire as well as the 3D printed. That means from the spool whatever we have generated, the customized the 0.1 weight percent to 0.2 and 0.3 at weight percent, and with the natural. What is the electrical resistivity or maybe the thermal so electrical conductivity we did, and some of those investigation to see why those mechanical properties are increasing or decreasing, are supported with the EDS and SEM and UES analysis to know whether the CNTs are being dispersed or they are agglomerated while depositing the material has been done. So this is the specimen size dog bone shape which was created in the 2D, and then the 3D model was built with the thickness 19 millimeter, this one 4 millimeter thick. And similarly for flexural test, we had ISO 178 specimen size using ASTM D638. We developed this drawing, and STL files are created, and then it was built in the 3D printer with the dogboard kind of shape, what we have seen over here, dogboard shape. Okay. So, flexural testing also we perform later on after building of this. So, we have the facility material characterization full-fledged testing center at VJTI in my lab. Cambrian Center for Advanced Material Research and Innovative Manufacturing. What we do the material development, 3D printing, and we do the characterization of material for mechanical and electrical. We have in our VJTI laboratory to do the electrical characterization. So this is 100 kilonewton capacity of machine to do the full tensile testing using the extensometer. Also, we have the strain gauge facility using the Koya data acquisition system for this particular material characterization in the on the UTM machines. So this is how the 3D the flexural test will be also conducted using the roller 3-point bend test using the fixture available in our laboratory. So we can do it. Then what we did, we pulled the specimen under the tensile test and we plotted the graph for force versus displacement. So a natural material, what we see over here, the blue one, what is shown over here, and then we had the 0.1, 0.2, and 0.3, percentage weight percentage of the specimen which are built. So totally 3 into 4, 12 specimen we pulled, and one of that category has been taken over here for force versus displacement graph. So if you look over here, energy under this curves or the area cover under this curve is nothing but the more energy taken to fill the specimen has been shown over here. So natural ABS without adding any kind of carbon nanotubes has taken less, whereas the 0.1 has shows the highest improvement, whereas adding with the 0.2 and 3 has shown the less improvement in the tensile properties. Some of those failure specimens, what we seen from our testing, look like consistently they failed within the gauge length when they pulled out in the UTM machines. So if you compare those, maximum tensile strength improvement, what we have seen with the natural ABS was 21% of the tensile strength of the same material, adding with the just 0.1% of MWCNT in the ABS, which was printed using the 3D print, phase deposition stereolithography methods. So those printed materials, 3D printed materials, have shown 21% of tensile strength improvement by just 0.1. But after adding the higher percentage, weight percentage, like 2 and 3 weight percent, it has shown the declining from the 0.1%, and that we investigated why it is declining, and we did the EDS and XRD, EDS and SCM images to see whether the CNTs are really dispersed in our material, and it has been made a good bond between the two layer, or any kind of air pockets or any voids has been created, has been shown. Same thing with our flexural test shown the decline in the property since the material was becoming look like brittle one in nature as compared with the ABS. So the highest brittleness what we have seen in the brittleness with the 0.1, 0.2, all have shown the less. But if you compare the area under the curve also, it shows but brittleness has been increased, and flexural test has been flexural strength of the all three categories, 0.1, 0.2, and compared with the one natural has been decline one. Then after comparison, how those 0.1 has been decrease 15%, 2%, and then continuously decrease. We also did the electrical test using the 3 probe method. So the setup available in our laboratory to measure the what is the conductivity. So we measure conductivity in terms of S upon M. So that's what the natural ABS shows, 5.1 into 10 to the power minus 8, and then point 1 has shown the 8%, then point 3 has point 2 has shown the 63%, and point 2 and 3 consistently has shown very high conductivity because of the highest carbon atoms and the conductive, because CNTs are the conductive in natures. If you maintain the chirality in terms of the maybe having the it can act like the both conductive material insulator. So if you have the conductive in nature, therefore the NWCT what we purchase from our vendor has a higher conductivity, and therefore it has implemented it has indicated in our thermal conductivity electrical conductivity test with improvement in the highest conductivity of the material. So if you look over to the each of those resistance plot, reciprocal of the resistivity is the conductivity. So with the applying different voltages, the resistance has been more. So at 15, those highest conductivity has been found out with the point 1 and this one. As we keep increasing the voltage, the percentage of at point 3 has shown the highest sometimes if you look over those dispersion and all those things has an important role, and therefore these graphs has given some idea the dispersion and agglomeration definitely might have been happen, and therefore these graphs are applying with the different voltage has shown that variation in the resistance of those 3D printed as compared with the ABS. Then we did the SEM analysis at SIRCOT and other facility available nearby us. So these are the specimen put on the spokes, and using the SEM, what we did to see is there any kind of spokes, any kind of voids are also there, or not bonded properly layer by layer, or curing has not been done properly. So those are the voids what we have seen. Some of those air pockets may play and decline in the resistivity due to the applied voltage variation has been confirmed. There are voids, and therefore it is inconsistent for the electrical resistivity. And why they are declining with the mechanical properties like tensile and flexural has been seen with the those kind of agglomeration might have been happened. So we did with the lower end of the presence of CNT what we have seen the SEM images before we put the CNT in the school customization. They had the nature of like such kind of forest kind of MWCNTs, and those MWCNTs at the lower scale we have seen the forest has been arrested in the presence of in the space 3D printed specimen. So this is the layer. In the layer we could see this is what the same kind of forest of the NWCNT has been observed over here. Uh, so using those morphological and EDS, we move to the EDS analysis to know what are the really the carbon atoms are increased or not, to analyze that one. So those CNT EDS graphs also help to know there are higher carbon atoms. Though the ABS is having the more carbon, but addition of the CNT has shown the consistently improving the presence of the carbon. So with this natural, we had the 73%, then adding with the 0.177, 0.279, and then again this specimen might have been agglomeration more. So we also seen, but not more improvement in carbon percentage. More is the carbon. Obviously, CNT is full of the carbon, so therefore we treated. There are presence of the CNTs in the ABS material, and therefore it has improved the electrical conductivity, and some of those improvement what we've seen up to the point 1 has been seen over here. So therefore, by adding the 0.1%, almost 22% of the mechanical tensile strength has been improved. Flexural strength dropped highest by 15% by adding MWC and T. And those agglomeration may be the possibility of occurring in the 3D printed, or maybe generating the spool. The dispersion may not be proper due to the heat, and we could not do any kind of surface treatment or surface preparation. So because of that, there could be a possibility of more agglomeration, and therefore we found the reduction in the mechanical property with increasing the weight percentage of the NWC and T in that one. Electrical conductivity has shown the improvement due to the presence of multiple carbon nanotubes, which is conductive in nature, and therefore conductivity has been improved over here. This is what we have done for the our multi-wall carbon nanotube in the ABS. Now the same material as a base what we have taken for the nanocomposite to again print using the graphene. So we also purchased the graphene. This paper is also published in 2018 Nanocon. This is I'm presenting from the same work what we have presented in that one. So here also what we did the only customized a spool with the help of using the graphene we selected for this study. So as we say, in the graphene is having the highest mechanical properties, incredibly very strong than the all other material. Tensile strength 130 gigapascal, which is 250 times higher than the other steel, and therefore can we put some of the weight percentage of graphene, 1D 2D graphene sheet, nothing but your single layer of the carbons, instead of having your wall kind of tube kind of nature. So this is what we have, the hexagonal honeycomb kind of lattice 2D structure. So it has the highest thermal conductivity, electrical conductivity Siemens per meter, and those materials we bought, those kind of multiple carbon nanotube we bought from again from our vendor. It looked like such kind of sheets we were having, but we could not do this kind of atomic level of imaging. So we had a uh, graphene looking under the SCM at 100 nanometer scale with this kind of structure, and we mix that one again with the using same mixture, having the ABS material, the material system followed with the same way like what we did in the previous multiple carbon nanotubes. The same mixer we mixed it with the graphene, and then we using the photonic at the solid space we produce the spool using the again the extrusion method of having the diameter of 0.15. So same like it pass through this mixture, they heat it and then pass through the different extruding temperature zone and pass through the water tank, and then we get the spool at the outer at the end having 0.175 millimeter diameter, and we wind it down the winder. Okay, so this is how my student he personally worked with preparing such kind of spool, putting the after mixing with the that roda mixer, he is pouring that entire in the hooper of that extruder machines, and this is how the extruder machines they extrude it, and then finally we could wind it the spool like this one. Can you see the spool over here? Okay, so that was done with the help of motors, and we had our customized spool with that. And they also printed. He also printed the specimen for both tensile as well as flexural testing using the same concept of ASTM D638 and ISO 138 of having 4 mm diameter STL file, same STL file we use to prepare for the ABS with the graphene, and then we did the testing for both with and without uh, 3 weight percent of graphene for the mechanical characterization to analyze the tensile strength and flexural strength. So if you see here, we had a very low weight percent, low natural ABS had shown very low strength, whereas if you compare with the point 0.1, point 0.2, and point 0.3, so up to point 0.1, it has shown the highest, increase in the strength, which has been shown over here. So the maximum tensile strength, which shown over here, was 30 megapascal, 30 as compared with your 24 megapascal of your natural ABS, and that is the mechanical tensile strength has been improved by adding the graphene in the 3D printed what we developed using over here in the FDM processes. Then we also did the flexural test, and natural has shown the higher, more flexibility, rubbery nature. By adding this one, it has reduced the again the rubbery stage, or maybe the more elasticity has been lost, and brittleness in the material has been built into the addition of additional graphene seeds, which has been might have been agglomerated and resulted into the decrease in the continuously flexural strength as with comparison of your base material. These are the some of those images what we have captured for the natural ABS, and this is with the point 0.1 weight percentage with the cross section of hydrolyzed specimen what we have seen, and then adding with the point 0.2 and zooming it to the more lower scale, what we have seen there is a 24% of the presence of wall, the seed can be a possibility of TM may resolve the presence of your graphene seed, but SEM we could not capture, but we could see the surfaces what has been built with the increase in the strength has been shown the rough surface. That means they have made a very good bond due to the presence of graphene in the ABS while 3D while printing those material using the customized spool has been resulted. So 0.3%, 24% of significant improvement has been shown. That 7% is a decrease in the flexural strength has been observed. There may be the possibility of printing angle is at 45. So if you change the printing with the 45 or 30 or maybe some other angles, maybe only the line also if you print it horizontally, it may have the better improvement in the tensile strength, because there are possibility of having the continuous layer in that direction. So the angle also longitudinal specimen axis has to be made, and then it can improve the further mechanical and electrical conductivity in that one. So this is what they printed, but analyzed that because of this kind of layer, there are possibility of having weak bond between those bottom layer and top layer while building the entire width of 4 millimeter, might be the possibility of losing the mechanical strength has been identified in this study. Then, similar to the previous experimentation, we did the EDS analysis to find out what are the carbon percentage in it. So it has shown the graphene percentage. Graphene is a single seed, but want to see what is the weight, atomic weight percentage of carbon. 73 in the ABS, and then it has increased by with the 0.1%. 78, 77, and 76, some of those report what we have seen from the EDS. Maybe the agglomeration, maybe the possibility while selecting the specimen for the EDS analysis, and therefore we could see some of the reduction in the point 0.2 and point 0.3 has been identified in the EDS analysis. So energy dispersion spectrum has shown those, but there is a possibility of choosing the specimen plays an important role to analyze and see whether the carbon atoms are more or not. That is been seen from this analysis. So this is the electrical conductivity test. Again, same setup, and we compared the ABS graphene for the calculation of the resistivity test. So percentage of 0.2 has shown the highest improvement in the uh, resistivity. Lower the resistivity, what we have seen here. Those voltages, what we have seen, uh, resulted into the those different temperatures. So at point 40, what we have seen over here, for all those 20, the lower resistivity has been shown. That means there is a higher conductivity, electrical conductivity is possible. And if you compare those, trends of the conductivity as a reverse of the inverse of that one. So with adding of point 0.3 has been shown the highest conductivity Siemens per meter has been shown over here, which resulted by adding of your graphene has more effect of improving the electrical conductivity as well as improving the mechanical property has been seen as a compare of these two studies. And particularly this conductivity was tested for the 15 volt, and this has shown the highest conductivity for adding 0.3 weight percentage of graphene in the ABS by using the FDM 3D printing of the uh, graphene with the butadiene, acrylonitrile butadiene, styrene ABS material with adding of this 0.3 weight percentage has been shown the highest improvement. So this can, has the, conductivity test, which shows the, increase, which may be the cold. What we have done, the again those printing angle with that one plays an important role to improve again the conductivity. If you have the layer like what other experimentation I am going to discuss, will be coming to know what are the angle of deposition for the generation of G code and M code, which plays an important role in the 3D printing of those material. So the final conclusion: 24% weight percentage by adding the 0.3 weight percent of graphene and the reduction in the 7% of the degrees in the flexural strength conductivity is suddenly improved. There could be the some imperfection in the FDM process like voids, curing. The natural curing has been UV curing has been used to solidify quickly, but there is a possibility of some more bonds in between the two layers might have been left. So that is the one of the possibility. By adding more, it become more brittle material in the flexural test, and therefore not advisory in the more weight percentage in the flexural, material where there is a more flexure, flexural load occurring on the material can be the one of the outcome from this research. To increase the conductivity opens an opportunity application in 3D printing for the electrical circuit boards. So if you have the more conductivity, so you can restrict the conductivity property, and if you are using this material as a cover or maybe casing for certain products, so we need to think about whether to use the non-conductive graphs, non-conductive MWCNT or graphene has to be taken care while selecting the material to print and customize it accordingly has been one of the outcome provided by this research. Uh, Increase in the strength and stiffness characteristics and those intricate shapes and can be a possible, and therefore it may have potential in the aerospace and automobile industry to improve to incorporate such kind of material for the interior part where TGA and other thermographic analysis we could not do, but what is the weight loss and all those can be seen that we have done in another study, but not over here. Uh, this is very interesting what we have published recently, the paper in the SAPI 2021. Uh, what is important over here so far is we can print and we can have your G code, M code, print it and develop your speed, then deposition layer, their thickness, all those plays a very crucial role in the photo curing method, or you can say the polymeric material like thermoset and thermoplastic. But few of those, important concept what the people are playing around in the 3D printing is what should be the infill pattern and what should be the percentage of the infill. Shall we print the material with 100%, 70%, 50%, 30%, or 20%? And what are the patterns? Whether we should use the rectilinear, triangular, hexagonal, grid patterns, or honeycomb? What kind of patterns will improve the mechanical properties? That is very challenging, and very few people are working on that one to develop such kind of 3D printed material. So what we have tried in our this research is effect of infill patterns on 3D printed multi-wall carbon nanotube based ABS material. The same material what we have discussed in the first presentation of the first is the experimental part. The same kind of spool methodology we used, and we develop our material, and we we try to use the another methods to develop those 3D printed materials infill patterns. So what is the percentage of the infill we can use? Whether you want to use like say 10% or 15%, or what kind of percentage you want to use. So the percentage of infill is very important, like 100 percentage or 50% you want to use, or maybe any other kind of percentage you want to use. And the grid patterns, what we talk, like we have the rectangular grids, you may have the triangular grids, you may have the hexagonal grids like this one. You can use the grid and see whether you can achieve it, or any other kind of grid patterns you can use. So in this study we have used a different kind of grids patterns and percentage in fill. So 50% or 20% you want to use as a fill. So that, because the infill pattern percentage fill is also playing important role to reduce the material weight, reduce the structural entire weight and the consumption of the material. If you are using the very costly material, can we use the different patterns so that they can improve the mechanical property and reduce the weight, and reduction in the weight will definitely help us to reduce the consumption of the material, which is a costly material. Wastage of material will be reduced. And how do we improve that one? Using incorporating some of those, or addition of the some of the nano material in the existing material, and start building using the 3D printing, whatever the either you are using metal 3D printing or polymeric 3D printing you want to use, and either a top-down approach or a bottom-up approach you want to use, and build the structure, and those one has been discussed in this study. So there are three different fill patterns with the volume percentage we have considered in this study. So if you see this, weight percentage 0.1, 0.2, we have taken to see what are the because they have given some improvement in the early study. So we move with the same weight percentage. We again generated the new spool, because what we have studied in our study, this experimentation and research at VJTI is ABS has the self degradation life because of the adding of those LWC and T. If you don't use it for the spooling, so we are unable to cure it if you hold the material, because ABS has the property to absorb the moisture, and it degrades self. So to avoid that one, we need to take care of consumption of that spool whatever we have customized in a stimulated period of time. So those things we have observed in our research, and we move in the next level of research by selection of infill patterns and percentage of infill in this study. And then conventionally we do the mechanical characterization and identify whether they are improving any kind of material properties or not. That has been seen from this study. So Let's go with this particular study. What we have done, the mechanical characterization improvement so far using the SAMPE's 2019 early result. So we seen this particularly, 15% of improvement in tensile strength. As we keep adding, so this these properties are properties are decreasing continuously. Okay, so this was the base to think about what kind of infill patterns we can use. Okay, so this infill pattern with the infill percentage is the important uh, part of this research. So that has been help us to go ahead with the available research what we have done with the done by the various researchers and people published the research on this infill patterns and percentage. So we map with their existing selection of the infill patterns and their percentage like full honeycomb, grid, rectilinear, and triangular. So these four infill patterns we selected, and three important fill patterns like 100%, 50%, and 20% density volume percentage to has been selected to see what kind of mechanical and electrical properties can be obtained. So in this study, what our goal was to see whether we can obtain any kind of improvement or enhancement in the mechanical and electrical properties. What material systems what we have designed and printed using the 3D printer is same 0.1%, 2%, and 3% base was being laid in the early research of 2019. So we incorporated full honeycomb, grid, rectilinear, triangular patterns with 150%, 20% infill. This was repeated with the both 0.25, zero point 0.2 and zero point 0.3, and natural also. So this was been the material system initially we selected for this particular study. So this is very important as a research plan for this study. So this is what we have the cortex. The second spool we manufactured using the extrusion methods, and we also bought the new material from the vendor, and we did the SCM imaging before we use it to see whether really a good multiple carbon nanotubes forest has been available in the images or not, has been seen at a different scale in these images. So this is what we have done. There are clearly indicating there are multiple carbon nanotube forest is shown over here. So using this, when you melt the natural ABS, it look like a watery kind of color, very thin. And if you do the weight, if you take these pallets and last time what we mix in the pallets with the hot weight percentage, and you can also see if you drop it inside your liquid one, it look like this kind of liquid with this one. But here you can see the palette with after mixing it is looking like that one. So heating zones they set, and then extruder pass through that one, and then we obtain the 3D printed customized filament of 1 2 3 of point 1, point 2, point 3, and natural ABS like that. So what we built, what we developed the method in the 2019 experimentation. So we printed the three specimen like this for natural ABS, very clear and crystal clear and high quality of curing. We taken care by setting the environment chamber of the 3D printers, and then we also did the particularly those lectural specimen also printed. So this was the initial base what we have laid down. Now let's go with how do we create the STL file with the different grid patterns. So infill patterns for the FDM 3D printing materials, which is a lot of people are working on that one. So what we developed over here using the 3D printing SolidWorks uh, CAD modeling. So we created this kind of honeycomb structure first, and the STL files were created for the honeycomb. If you look over here, honeycomb, hexagonal kind of natures, how it can be accommodated. So this is what has been seen over here. Rectilinears, so those are the grid patterns the STL file created with the and passed to the 3D printer as the STL file, having this kind of three number of samples to be printed using the natural ABS point 0.1, point 0.2, and point 0.3. Rectangular, triangular grid patterns also has been created, and that same STL file has been, pattern with the three number of specimen and passed with the grid with the this kind of structure has been created, and the fourth one was passed. So the three important, so these four important grid patterns we have selected, and then it passed for the building of those material. So when it was selected for the printing, so you can see some of those specimen without any grid pattern, full 100% also can be seen with the flexural as well as the tensile, which was built with this kind of uh, structure. So the top and bottom layer you can make with the full with the 45-degree of printing of those G codes has been selected, continued with the same experimentation for both tensile as well as your flexural testing, printing of this one. The volume percentage, what we have seen, if you look for this 20% volume, we selected, and then 50% volume, the STL file looks like that, and 100% volume is a fully covered with this one. So the same files what we have generated with the three volume percentage 20, 50, and 100 for each of those each of those patterns like honeycomb, rectilinear, triangular, and grid has been generated and passed to the printer to print using the customizer customizer three spools with this kind of specimen. So if you look over the cross section of the infill pattern, which is shown over here, the grid, you can see those patterns with for the ABS, and similarly for the your multiple carbon nanotube, point 0.2 and point 0.3, 1 to point 0.1 to point 0.3 weight percent is also printed. So these specimen we tested using our strain gauge data capturing method, as well as to calculate the what is the Poisson's ratio we can achieve in such kind of grid patterns and infill method. So this is what we have the strain gauge data acquisition system. So we had the 5 specimens and then blew it, and we captured the Poisson's ratio and modulus using the this particular data acquisition system using the 100 kilonewton Simazus UTM machine. So by performing this experimentation, the tensile testing of the 3D printed samples, what we have seen with the percentage infill, pattern selections. So this table shows if you go with the rectilinear with the maximum tensile strength, what we have obtained with the 100%, 30 megapascal, 25, and then again 25. So the infill pattern has not made any kind of effect on 50% and 20% infill in your rectilinear natural ABS. Okay. Similarly, if you go with the this is for the natural ABS, you can see. So this natural ABS can be uh, for the grid also. So we printed with the 26, 25 was the tensile strength. Full honeycomb also 26 and 26 point little higher. The 30 and 28 has been seen as a reduction in the grid pattern tensile strength of all four in, with reducing the volume percentage of the infill in the all those has been said. Now, what we have done with the uh, zero point 0.1 weight percentage, we did the tensile strength for the this one. By adding with this, it has been improved by almost like 6 megapascal higher, and their corresponding deviation to see whether the material is consistent or not. So 25% again reduced 20, and so the tensile strength is reduced. Even though we add it, it become again reduction in the tensile strength. So like that, in each of those cases, the tensile strength for zero point 0.1 uh, has been consistently reduced by reducing the volume percent and weight percent. Selection of the pattern also infill pattern. Rectilinear triangular, so 23. So in triangular, we could not see any drop over here. It has shown the consistently. Here in fully honeycomb, you can see uh, 22, 20, and 24. So it has been shown little improvement, but we have already done some of those imaging and see whether really it is improving or not. Now, if you compare with this, so it is drop consistently drop with the point 1, point 0.3. So with 100%, so it is again reduced with the rectilinear or grid also. The infill 100% with 20 is also reduced with the natural. That means it becoming more brittle due to the addition of the multi-wall carbon nanotube. Though we have the infill patterns and the weight percentage, our goal is to reduce the density of the material. That means overall consumption of the material. We tried in this experimentation and tried to see what kind of mechanical properties we can improve it. So the grid patterns, the second improvement what we have seen over here as compared with the uh, your remaining point two little improvement has been shown. Uh, Fully honeycomb also improvement has been shown. So this is a fill pattern rectangular grid honeycomb and triangular with 100%, 50%, 20% in each of the category we have seen and compared their corresponding mechanical strength in the three weight percentage of NWCNT of the 3D printed material. So the rectilinear, what we have seen, 100% has always shown the highest strength with zero point 0.1. Rest all has been reduced. The same, interpretations of the table has been more clearly given over here in the in whether it has improved or reduced the 100% and uh, 50%, 20%. So consistently by adding zero point 0.1 and 1 has shown only in the rectilinear improvement with the 100% as compared with the rest. As compared with the EBS with point 0.1, they have shown almost the same tensile strength. But if you keep increasing, that property has been dropped with the infill pattern also. That is the first conclusion what we have seen from this. In the similar to the grid pattern also, there may be the chances to having the grid organized in the tensile axis, longitudinal axis. Therefore, the properties has been reduced from 26 to 23, then 20, 21 like that one with the adding of point 0.1, point 2, and point 0.3 with the three infill patterns like 100, 50, and 20 is consistently reduced. Similarly, in the triangular kind of fill pattern, but we have seen the drop in the mechanical strength, that is the tensile strength with the 100%, 50%, and 23% as compared with your natural ABS with the 100% fill. So here, point two also it has been dropped or moreover it remains same in the 100%. But as you keep, you know, increasing with point one, point two with the where reducing the fill percentage, they have decline in the tensile strength of uh, the 3D printed material in all the four ones, except point one has shown the little improvement that's uh, has been shown over here. Uh, this also, if you see from this, the comparison of the grid patterns with the those color, point one, point two, point three. So point one has only shown the improvement. Grid, no substantial improvement, no substantial improvement, almost very small improvement we have seen uh, in the full honeycomb triangular also. uh, we have not seen any significant improvement. It has little decrease in the mechanical property with the selection of the infill patterns with NWCNT in the 100% filled material. In 50% also, if you compare those graphs like 25, if you go with the 26, 26, so those naturally, what we have seen in ABS, with those, they have shown very good, properties with the triangular one, which has shown the 31 over here. But in other patterns, they have dropped with the 50% infill, they have dropped it. But overall, if you look over all those comparison with the 50% also, by adding those multiple carbon nanotubes of point 0.1, point 0.2, and point 0.3, the 50% infill pattern with the grid 50% infill with the patterns consistently, they have declined the property, except in the rectilinear, they maintain the same one, but remaining all has been declined the tensile strength of the material. Uh, this particular nanocomposite. Infill patterns, look over here with the 20% also, 25, 25, 26, 28. Triangular has shown the highest, same triangular has shown the highest in 50 and 20. But if you look over here, let me take the color and highlighters. So here, uh, if you see this particular figure over here, okay, let me go back here, and in case of this 21 over here, if you look this particular one, they have shown the improvement in the triangular with the natural ABS, and it has very less effect, though it has declined by adding the NWCNT point 1, point 2, and point 3, but consistently 20% fill pattern, 50% in fill pattern. Adding up CNT won't improve the more tensile strength, but this grid patterns, uh, triangular, both in the 100% field and uh, in case of 50% and 20% has shown the improvement in the mechanical strength, but rest all have been declined, and therefore it is very difficult to choose which pattern and which percentage, field percentage, and which pattern will be best suitable. And we tried to see whether there is any kind of effect of improving the mechanical properties, though we have reduced the wind field pattern by adding the NWCLT, has been shown in this study. So point one has only shown the rectilinear with 20% improvement in the tensile strength, but point two and point three has reduced drastically the mechanical strength in 100% infill pattern of the uh, nanocomposite with ABS. Also, in the 0.1% rectilinear, which has the highest mechanical property, natural ABS with if you look over here, particularly in this column, 30%, 36%, 30%, and 28% are the improvement what we have seen by using these three important uh, patterns, rectilinear and triangular, has helped to improve the properties in this entire study has been seen. Some of those failed coupons what we have seen and obtained those SEM images has been narrated over here. So 36 is a megapascal. Rectangular has shown the 30 megapascal, and 20%, 50% and the 20% has shown the 30 and 28% of improvement. Highest mechanical strength has been shown. When comparing with the infill patterns, shows satisfactory in the tensile strength, whereas there is no significant improvement has been seen. Zero point 0.2 and 0.3% of specimen weight percent of MWCNT with different infill pattern has consistently degraded in the tensile strength and cannot be correlated with the past experience, experimentation what we have done in the previous research also. So this is what the 22% improvement and 100% infill pattern and triangular element have the better chances to improve the mechanical properties. Uh, this is what is from my side. Now I'm going to take you through the current prospect and future, challenges coming for the 3D printing. This is from the Lockheed Martin, one of the paper where I was been the one of the session track, session chair, as well as the chairperson for the track of this particular one. So I choose best of the material, best of the work what so far the currently available with in this trend of 3D printing. So this is from the Lockheed Martin. Bob Boone and is the author, and his group has presented. So I'm presenting from his paper, what is been published into 2021 proceeding of SAMPI. So as we see this is what this research talk about the continuous fiber 3D printing process. Now we have manufactured the conventional composite fiber reinforced composite using the different patterns in patterns of the view forms like plain, satin, then other braided and all those things. So we let stack all those stacking, and then we put under the vacuum bagging or maybe a mold, and then we infuse number of inlet of the infused resin, and then it occupies the entire surface, and finally it makes the complete composite structure. So how to do the continuous fiber 3D printing is the main goal of this paper. So development and application of this particular technology I'm going to discuss in this one. So there are certain disadvantages of this, to improve the interlaminar shear strength of the laminated composite by using the different innovative methods such as chip cleaning, damage tolerance registers, 3D weaving, and braiding. One of the paper what me also and my research has already published on in modifying the resin by incorporating the nanomaterial and nanofiber in it has improved the interlaminar shear strength, making the strong bond. So those are the methods has been developed. So the continuous composite by Hoyer D. Allen RD is called as the continuous fiber 3D printing, which is a registered trademark of the Lockheed Martin Manufacturing Center. So this method was developed, as a small business of the additive manufacturing in the mechanical, drawbacks of the extrusion processes have been taken care over here. Because generally our extruder gets stuck or clogged due to the passing through the impregnated fibers which are passing and printing the single fiber and developing the unidirectional 3D printed fiber reinforced polymeric composite. So these are the mechanical advantages, the drawbacks of those infill printing with the extrusion has been occurred. So no fibrous reinforcement continuously you can print it using the current existing 3D printers. So what they have developed, the new method which came in 2015 is called as the patented technology called as the continuous fiber 3D printing method, which established in 2015, and some of those findings of the additive manufacturing is helping us to develop new facility of to reduce the manufacturing cost, tool cost, enhance the productivity, reduce the defects. So the recent efforts made at the continuous composite manufacturing in the cooperation with Lockheed Martin, sponsored by U.S. Air Force Research Laboratory, adopted this technology for the carbon composite continuous 3D printing methods. So what it is exactly? So in the current version of the continuous 3D printing, it has such kind of a completely robot boom, having a header, a big header incorporated with what we say the end effector and motion. This particularly the header what we see over here, motion platform over here, is having such kind of continuously 3D printing kind of head is available over here. So this CF3D is akin of the AF in that robotic manipulator and effector diverses the impregnated toes. So remember, students, these are the toes which are coming in the form of strips impregnated with the resin, which pass through the this big extruders of the toes in the form of tapes. So those tapes are deep in the resin bath and they pass through this extruder, and then they place layer by layer and curing by UV curing. They use in the CF3D header attached at this fauna motion over here. So this is how a layer by layer can be deposited, and you can build the structure quickly by using continuous 3D. This is carbon epoxy 3D printed composite over here. So what happens in this one is this is a very simplified process shown. I'm going to show in the next diagram with the executors, with the several those kind of state of art has been shown over here in the Lockheed Martin manufacturing. So what are the development has been occurred over here is one is the material development, and second is the software development. So these two development has made the changes in the continuous fiber 3D printing methods. So what is the material development is the photopolymer chemistry, which is the UV curing method, 3D printing method of the matrix has been chosen for this particular carbon fiber composite. This method has mostly deployed using off the or cell fiber, so cell fiber solution, including the various grade size of the carbon fiber, glass fiber, ceramic fiber, armide fiber, which is called as Kevlar or Spectra or Xylon. These are the market name. Is a well-known function fiber like conductive, a single core through the wires and fiber optical cables and exotic those R&D embedded electronics also they are using this materials right now. A few of those software development by using the techniques finite element analysis like topography optimization or finite element analysis before it go for this slicing or maybe depositing those tapes. So we are depositing a tape, one tape, the next layer will be the another tape, third layer will be the third tape, like that, and keep building the thickness of that particular structured component. So CF3D software analysis, which involves the physical, geometrical, and mechanical material characteristics to create and validate the motion at early stage. That is what the topology geometry optimization will happen. So how does this method, work in in that particular header ejector? What I have shown in the infrastructure state of art available for this continuous fiber 3D printing is what we have here are the dry fiber in the form of spool, carbon, glass, Kevlar, metallic fibers, or fiber optics. This will be wounded on a spool. So this may be a tape, this may be a single fiber. So dry fiber, which comes in a, it dips in the resin bath. It passes through like this. So this is the resin bath, which pour the resin continuously maintain the supply of the resin, which will be maintained. So this fiber dip over here pass through the other end like this one. Okay, so this is a semi-cured resin is here, and therefore whatever the resin is being observed by this dry fiber will be coming as a weighted fiber or a tape, and this tape pass through the roller and it stamp it on the substrate, and subsequently your laser UV light or heat source will be allowed, impregnated or incinerated. So incident light or maybe exposed light of in terms of your laser or maybe UV light over here, and then this particular portion between this to this is get immediately cured. Okay, and then this particular roller this roller will be moving in this direction like this. Okay, and this is how the part surface been deposited, and you will be having first layer will be deposited on the substrate. From this to this, your first layer will be deposited. Okay, and you can use any resin, maybe thermoplastic or thermoset over here, so that the energy source will be a different over here in this continuous fiber 3D printing. So if you are using the thermoplastic, you use the UV and immediately cure it, solidify it. You can also use the UV or the heat source to solidify the thermoset resin, and you can keep developing. And that's what we have printed over here. The layer is deposited, and immediately the whole section is having the UV curing. So slowly it is printing and moving to the last end of this one. Okay, so like that we can build it using this kind of continuous fiber 3D printing method, which is very important. So it has a various application right now in the aerospace. So it has the challenges, but offer a clear cost and performance advantage, because no tool is involved, no rework or chances of occurring the defects has been reduced, man intervention has been reduced, fully controlled robot automation has been done, and therefore it has the mature production program require considerable returns on, because the robot booms has been involved. So it has that only investment before considering the replacing of proven technology, that what Wharton method we have or H Wharton method we have, and autoclave and out of autoclave methods we use for the 3D printing of the large structures. So ideal transition from the platform is new, low cost, and would currently be a conceptual right now in the conceptual design phase, and will benefit for the 3D printing of the continuous fiber in coming days by including automation, less tool processing, low cost of raw material, and high rate of material deposition by using this method. In US Air Force, they have already established the low-cost artillery aircraft, what is called as the LCAA program, that calls the development of the entire structure of the aircraft by using this kind of technology, which is called as unmanned air vehicle. Unmanned platform can be directly working. Unmanned platform can work to build the entire structure of the aircraft with the low cost and high, accuracy and high manufacturing performance will be obtained in the coming futures. So you can see those kind of coming Lockheed Martin LCA, which aircraft will be coming in near future, very soon. We'll be having such kind of various kind of aircraft which will be having this kind of continuously fiber reinforced with 3D printing method can be used to develop the entire structure in the one umbrella of 3D printing facility, which is under the development right now and will come very soon as a vision vehicle like this one in the near future. Few of the challenges in 3D printing, what we people are facing at such kind of manufacturability is having highly suitable with adhesive by the vision of this digital factory of the future. So now they are making a new term which is coming as a DFOTF, what they call as a digital factory of the future, in which the autonomous automation capability, having some learning robots which extend beyond, and pre-programmed instruction for to perform the manufacturing assembly task in the coming future. There are challenges, but this is what it is coming. It will enable in the robots to adopt the human interaction on the factory floor and continuous learn, but manufacturing processes without any kind of change is possible. So DFOTF is so central to the DFOTF is the use of digitally controlled manufacturing processes. Without such, the 3D printing thread running from the design through the manufacturing to the service life, and it's not a continuous thing made to the robots, but it could be programming in very near futures. The flexibility of this CF3D process offer unique opportunity for future composite design and capability for the cost-effective fabrication of the topology optimization techniques, and you can have the highly structurally integration in using the multifunctionality to such so, to the future, having interested in those one. So few of those manufacturing facilities, what the prospects of the 3D printing for the such kind of LCA, what the program have been launched by the US Air Force. The aircraft will be designed like this very soon by using the robots, and they will be building the structure very quickly and having very consistent manufacturing capability, and high manufacturing productivity will be built using this kind of the unmanned air vehicles, which will be going with the different Mars mission and Moon mission from the NASA. And so they are looking to develop such kind of small, tiny, and very small aircraft using this kind of the manufacturing capability with the zero defects and cost performance. So the future of the continuous fiber 3D is having topography optimization and functionality. So multifunctionality you can. So here whatever the structure we are developing, so you optimize it using the finite element analysis and 3D CAD modeling, and same can be passed to the 3D CF 3D printing method and can be obtained. So this is what the future is working. Some functionality can be provided on the same structure, like unique to insert the alternative fiber inside the dry structure tools to provide the functionally capability to the resulting composite structure. And you may have the continuous composite, which has already demonstrated this one, to embed the fiber optics and filaments and some nichrome wires as a manufacturing demonstration. So here, if you see, this is the what the structure has been developed. So it has a LED has been built inside in it. Fiber optics has been already printed in this 3D printed structure. Copper wires is also available here. Micron wires are also provided here. So this kind of integrated integrated components is possible in the 3D printing of those big structure for the aerospace application is possible. So the conclusion is 3D FD is a new class of additive manufacturing which enables the low cost manufacturing and high performance composite structure. It has through the design of unique robot and end effector continuous composites, which has successfully deployed and developed the ability to place the continuous fiber impregnated on the ply with the UV snaps curing, what I have shown in my image. This tool less features, and in combination with its fully automated additive manufacturing concept will provide the breakthrough in the cost effective composite structures, and ideally suited for the application in the new family of Air Force unmanned air vehicle design called as a low cost retrieval aircraft in the coming days. Future development will include the continuous improvement in the capability of resin, and then production design and end repair, end effectors, demonstration on the aircraft structure, including consideration of the advanced topography optimization and multifunctional capability in the for the structural integrity or beyond the structural integrity by providing such kind of multifunctionality on the structure. That is what we have seen from the 3D CF3D. The next one is I want to share. This is again from the Dong and his group. He has talk about the how to improve the large scale additive manufacturing of high strength fiber reinforced polymer composite by using BOM. Big area additive manufacturing is the area people are developing big structures in the manufacturing sectors. They are using this method and providing the use or developing the state of art for the 3D printing of large structural component printing right now going on. This is what we say the BAM, BAAM, big area additive manufacturing. So the commercially single extruders may be used to print with this kind of multi-axle machines. So Galaxy or automated precision or maybe having your 3D printed in X, Y, Z direction, you can have a unique motors and heating capability, you can provide this. So experimental setup which shown over here will be having your carbon fibers will be coming, then your axis in X, Y, Z, the 5-axis machine 5-axis controller you can have, then extruder headers with the different axis and printable beds you can do using this kind of uh, uh, big area additive manufacturing, the advanced additive manufacturing. So experimental consists of extruder, printed head, multi-axis machine with prospective controllers is shown for the some of the printing for PLA materials. In this experimentation, what they have talked about the PLA. So how does it work? Like continuously extruder having its own feeders and printing rather than having the spools and all those things for the big area additive manufacturing. So you have the printing bed or substrate you can say, and the deposition of the composite what continuously flowing like this one. So the pallets will be coming from your hoopers and directly entered in the extruders will be feeded at your header of your 3D printers. So heating coils and those heatings will be those molten metals. Another intervention or intrusions will be done using the continuous fiber toes, and those toes will be impregnated with this kind of pellets, PLA pellets here they are used, and they are also depositing with the printed bed or the substrate with the help of this one. So this is a different motor they will use, and they have developed such kind of big structures by using the large format additive manufacturing for the filament, and they build the structures like this. You can see how the curing has been occurred. Those internally structure support has been given for this kind of thin wall PLA with the continuous fibers, carbon fiber with the PLA in the bottom. It's been shown over here in the B. So this is the fibers are continuous over here, but they have developed 150 millimeter of thickness of this kind of the airfoil shape. What they have been developed by using this large additive manufacturing area. So some of those thin wall structures using the short fibers or fiber ABS pallets, what I have already discussed in my experiment. So they are also using the same kind of extruders, and they are curing like this one and printing this kind of structures. So nose cone mold structure has been built using the extruder rather than having your autoclave or out of autoclave methods. So this area is also emerging and having the big challenges to the process controlling, and topography automation is the only thing, but that will come over a period of time, and you can have your continuous development. So in conclusion, the proposed manufacturing techniques based enables the rapid and inexpensive fabrication of the high performance complex structure using the continuous fiber reinforcement with an ability to rapid print complex and large net shape structures is possible. Uh, Also propose the additive manufacturing process is a cost-effective solution to the rapid fabrication of strong and inexpensive continuous fiber reinforced functional composite is possible from this one. So with this, what I do, I will stop over here. I have I already shared most of my uh, stuff over here, and I will be happy to take few of those questions. I have few material, but due to the time limit and other speakers in a queue and your break, I cannot uh, you know cannot take long sessions, but this is what I want to acknowledge JSNN and my center. These are my PhD students who are working in my labs. So these are the research scholars who working. Three of them are graduating this semester in the PhD program. Suhas, Sachin Kulkarni, and Divenka, they have submitted their thesis, and the remaining three are already working on their 3D printing and developing the nanocomposite using conventional way and recent technology. So I acknowledge my institute and JSNN for giving the opportunity to create such kind of research work with the available state of art technology with us. And with this, I stop over here and I will take the question. Thank you, one and all.
Thank you very much, sir, for your wonderful session on the 3D printing aspects in nanocomposites. Uh, it was indeed a very uh, informative session. So few questions we can take up from the participants. Participants, please feel free to ask if you have any doubts or questions, or if you have anything to discuss. Participants, you may write your question in the chat box as well. Sir, there is a one compliment for you. Very informative session, sir. Thank you very much from Rajkumar Wagmare
Oh,
in
thank
chat
you.
box. Yeah,
Thank you.
yeah,
So my contact details are already available with the course coordinator, Dr. Bole sir. So if
yeah.
you
I will share
any further any
your
kind
details.
of assistance for studying further in the 3D printing, or if you are really interested to work in this area, you are welcome to interact with us anytime in coming future. Also through write a email, write your queries, and then we may have discussion, and I may reply your query by email. But WhatsApp and phone call, I have very limited time, so I can't talk. But I will definitely answer your email queries if it comes in, from your side.
Yeah, yeah. I will share your contact details with the participant. Sure, sir. So, okay. So I request Sagar Dhotre to give the vote of thanks.
Thank,
Participant. Yeah, yeah,
huh,
yeah.
thank,
Go ahead, Sagar.
Thank you, sir. So, in the behalf of Sardar Patel College and the entire FDP organization team, a very heartful thank to Dr. DK Shinde sir for enlightening the topic on 3D printing of polymeric nanocomposites, that perspective and the challenges. Sir has enlightened the experimental setups with the material mixing for the filament preparation. They have also discussed the procedure for FDM specimen preparation on aircraft I-250D. Also, sir has discussed different mechanical and electrical testings. So, how could we can use mechanical testings like tensile fracture using 3-point bending test. Sir also enlightened the various experimental work. Then Sir discussed the extensive methods of nanocomposites to make a spool. Sir also have explained the resistivity test by using material and different combinations of ABS material. Then also different weight percentage. In the end, Sir has discussed the future of CF3D. What are the different challenges different challenges and the uh, for 3D printing and the future of CF 3D printing. Sir also discuss the large scale additive manufacturing. So thank you very much, sir, for enlightening the experimental knowledge in this field. Thank you.
Okay, thank you, sir. Thank you very much.
Okay, thank you. Good luck to
Thank you,
all the
sir.
participants. And shall I leave the meeting, sir?
Yes, sir. Yes, sir. Okay, sir.
Okay,
Thank you,
thank
sir.
you. Yeah,
Okay.
thank you.
So all the participants, we will meet for the last session of the day at 2:15 sharp. The feedback link is available in the chat box, and do fill the feedback, and then we will meet at 2:15. Thank you very much.